that, so the first condition A1 becomes that the probability that nu nj of u infinity minus nu u infinity is larger than epsilon goes to 0 for all epsilon positive and all u positive. And the second condition becomes the probability that sigma nj of u infinity is larger than epsilon goes to 0 for all epsilon positive and all u positive. And these conditions are, of course, stated for given sequences, for a given new measure, and for given sequences an and cn. So we have arrived at conditions that tell us that these quantities here must converge in probability to here a limit nu and here to 0. Okay, so what differs from the case of independent random variables is that the quantities that the new quantity that we want to prove converges is a function of our jump chain. So, and by contrast, in the REM-like trap model, this quantity was only a function of the random environment. But now it's a function of the jump chain and the random environment. So what is the idea to prove that this converges? Well, we know the simple random walk on the hypercube very well. And what I told you yesterday is that the simple random walk becomes stationary very, very fast compared to the exponentially long times on which we observe the process. So the sum here is a sum over an exponentially large number of steps, while the jump chain becomes stationary in essentially n2 steps. So the idea is that in this sum, if I look at my sum every n2 steps of times, what I see here is a chain that is essentially equilibrated. So there should be some sort of ergodic theorem that takes place that enables me to replace this object here, this new j, by its expectation with respect to the law of the process j. So this is exactly what we will do. I will erase this condition here. So there is an unpleasant thing is that for the simple random walk on the hypercube, I cannot talk about the chain being stationary because it is a periodic chain. The hypercube graph is a bipartite graph, so the chain is never stationary because it keeps jumping from the odd hypercube to the even hypercube. So every odd number of steps, it is in one hypercube, one part of its bipartite graph, and every odd steps in the other cube. So actually, I'm talking about the chain being stationary because it's easier to say it, but when you do the calculations, you cannot prove anything like that. So let me tell you so I will call this a mixing property to avoid using the word stationary. So set kn equals 2n squared. Then there exists delta smaller than 2 to the minus n, such that for all x in Vn and all integer I, the sum over q equals 0 or 1 of the probability that starting in x, the chain Jn at time I plus kappa n plus q is in state y is equal to 1 plus delta n pi n y. So this is the right way to express that your process jumps from one of the part of the bipartite graph to the other. So that's how we can express the stationarity here. So in a chain that is aperiodic, you drop this sum here, and you have the definition of then what you get is that the probability to be in Y is exponentially close to its invariant measure. So this is the main property that will enable us to prove that the new J quantity here obeys an ergodic theorem. So let me write down this result. Yes, so what this enables us to prove is that the probability, so we are starting, you remember, yesterday I said we will always be starting in a deep quench, which corresponds to taking the uniform measure for on the graph for initial distribution. So we start from pi, and the modulus of nu J minus its expectation this is larger than epsilon with a probability that goes to 0 as n goes to infinity. But this is not what we want really, because we want to check our conditions. So that so far I said we fixed an omega realization of the random environment. But this is not enough for us. We want to prove that this is true uniformly in U, uniformly in T, and P almost surely in the random environment. So when we have this, we are in a good position because this result enables us to replace our new measure by its expectation with respect to the law of the process. I won't give you the proof of this result because it's a little bit long and delicate. It's not really hard. It really only relies on the small numbers of properties of the jump chain. The mixing property is 1. And you will also need to have a few more refined information on the process inside little boxes of size n squared, where the process is not equilibrated. So the information you need is typically the local time inside these boxes, some few things that we know very well because essentially we know everything we want about the simple random walk. And then, of course, it uses a lot that the random environment is IID. So let us leave this proof aside. Now, when we have this, then the conditions of Direct and Resnick theorems are reduced. Then, actually, these two conditions, A1 and A2 prime, A1 prime and A2 prime, are reduced to. So let us calculate this expectations here. So let me do it here. So I have to take the expectation starting in the measure pi n of the sum of, so fnu. Fnu is the sum over x in Vn of Pn Jni minus 1 x exponential minus u Cn divided by tau n of x. The expectation with respect to the law of the process Jn started in pi n. This is the sum over Oy in un of pi ny. And here I replace j by y. So p yx. So I have the sum over y of pi n y, p n yx. Now my chain is reversible, so this is equal to p pi n x, p x y. So let me do this. Pi n x, p n x y. Now, the sum over y is 1. And the sum over a and the sum over I, of course, is just a and t. And what I get is this expression here. So let me rewrite it cleanly. So what we get is that the expected value of f of nu and j equals the sum. There was a prefactor a and t. A and t, the sum over x in Vn of exponential minus u Cn divided by tau nx. And the expectation of nu n of sigma is dealt in the same way. And if you look up the lecture notes, so the condition now we get is that this thing, this expectation, let me call it nu n. So we can replace our conditions by these quantities here. So this means that condition A1 prime becomes, let me call it B1, becomes that nu n of u infinity converges to nu u for all u positive. And the condition B2 is, of course, the condition that, so it's defined in the same way, but you take the square of this quantity. There is a pi n missing, and this converges to 0 for all u. So if you compare with what we had obtained in the RAM-like trap model, you will see that these conditions are exactly the same as those we had in the RAM-like trap model. Exactly the same. We just replace the hypercube here by a complete graph, and you replace the taus by this heavy-tailed random variables that we had, and then you get exactly the same expression. And these quantities now depend only on the random environment, and the way we dealt with that was to use a concentration bound for IID random variables, Chernoff, Bennett, whatever bound you want, and prove concentration of this. So we only had to do that, and this converges to well, what it converges to, of course, depends on the properties of the taus. So the last thing we need to do to prove that our conditions are verified are some information about the taus. But this I told you yesterday already, that indeed on our chosen timescales, AN and CN, the taus obey a regular variation, a sequential regular variation condition, and of the form, so that this behaves like u to the minus alpha of epsilon times a certain constant. So this puts us exactly in the case of the Rem-Leittrap model on the complete graph. And so what we needed is just to recapitulate, apply our conditions of Resnick-Durret to these Z and I for fixed realization of the random landscape. First, gather needed properties for the jump chain, the most important one being mixing time. Second, prove a ergodic theorem, almost sure in the random environment, to replace your new quantity by its mean value with respect to the law of the jump chain, and reduce your condition to laws of large numbers in the random environment. Now, if you can prove a strong law of large number for these quantities, then you're done and you checked your conditions. So this is how we prove the convergence of the clock in the case of the random energy model. So let me not erase everything and tell you how we proceed in the P-spin SK model. And let me first remind you of the definition of the Hamiltonian. Start here. So in the P-spin SK model, so the Hamiltonian now is a centered Gaussian process indexed by the hypercube. With covariance matrix H and X, H and Y equal to n times the overlap between X and Y to the power P, where the overlap between the spin configurations X and Y is 1 over n, the sum from 1 to n of xi, yi. And if you prefer to see it as a distance, then it is equal to 1 minus 2 to the n, the Hamming distance or graph distance, call it as you wish, between x and y. It measures the discrepancies between the two configurations. It counts the number of spins that differ between the two configurations. So we now want to do the same thing. The dynamics is the same as before, the random hopping dynamics. So I just changed the taus here. I just changed the h in the definition of the Boltzmann weights by this Hamiltonian, which is now a strongly correlated object in the random environment. So how can we proceed now? Well, this choice of the Z and I is clearly not good, because there was a heuristics on the picture, which is on my USB key, but I think it will take time to put it on the computer and show it to you. So perhaps I make I make the picture on the blackboard. So, but I did not want to erase too much. Let me erase this. So yesterday we saw a picture of a hypercube, and I showed a big ball, and there was plenty of little dots that represented the taus that were of the order of Cn minus 1. Well, and there was a random walk, the chain Jn going through the hypercube. This thing has length a and t. And yesterday we saw that the set of Boltzmann weights that carry the set of vertices that carry Boltzmann weights that are of the order of Cn, they formed a Bernoulli cloud of size 2 to the epsilon n, so a huge cloud, but they were very sparse points in the hypercube, far apart from each other. So now, indeed, we are not in such a situation because we will have, essentially, the picture is that instead of having points that carry the vertices that are of size Cn, we now have whole lumps. And so what happens is that, so yesterday we had that the chain walked in the landscape and at each step picks a Boltzmann weight and sometimes hits the set of vertices that carry big taus. Now, indeed, the chain will walk across entire valleys that contain the taus that are of order Cn. So this is just heuristics and hand-waving things. So these are regions that are strongly correlated and that contains some vertices along the path that have exactly this size. Now, the shape of these valleys and their width is something that we can describe with precision. And these valleys are essentially far apart from each other and statistically independent. So the image we get is now that the clock collects, when it enters in such a valley, will collect a number of deep traps and then continue walking, and at some other time will walk across another valley and will collect another number of these big traps. And the clock will be formed not by, so the leading contribution to the clock do not come from wildly isolated, separated points, but they now come from entire clusters of points that you cross along the walk. So this definition, you can take it, but you will never prove that your conditions are satisfied. So you forget about it. And then we need another idea. And it turns out that that a useful thing to do in this case is, so what should I erase? I want to minimize the number of things I have. So let me, well, anyway, I will keep perhaps this. Let me erase that. So a good idea is to introduce a new scale. Let me call it beta n. I will use it to split my path into blocks of length theta n. And I will define the Zni to be the sum of the taus times Cni inside each block. So from so this will be block Zn I, and this will be a sum from J equals theta I to theta I plus 1 minus 1. And then I will define the blocked clock process SNT as the sum of, so let me put the normalization Cn inside. I will define it as the sum of the Zn I from 1 to a n t divided by theta n. So to simplify the notation, let me call k and t the ratio of a and t to theta n, and let me assume that a and t is an integer multiple of theta n because I don't want to carry remainders. So I write my clock as a blocked clock. Of course, I changed nothing so far. I'm just telling you that I want to make little blocks. And for these blocks, of course, I can rewrite my conditions. But the idea behind doing this is that if my mixing time, and this we know for the simple random walk, if the mixing time, if we choose the length of the block larger than or equal to the mixing time and very small to an, then by looking at the chain every theta I steps of time, then what I see is a sequence of essentially independent random variables, and well, and can hope that it will help me to extract independence from inside my problem. So let me tell you what our Gayrard and Resnick's condition become when we do these little blocks. So a few notation. So for y in V and U positive, so the price I have to pay for doing blocks is that now, instead of dealing with tails of single random variables, I now have to deal with the tail of sums inside blocks of length theta n. So tau n j n j a n j. So this is the tail distribution of the aggregated variables inside a block of length theta n. This is much less nice to work with, of course, than the tail of a single random variable, and I pushed all my problems inside dealing with these tails. So I know that I will later have to face this problem. So let me call Fn u of y the sum over x in V. This is the same definition as before, but replacing the tail distributions by these new quantities here. And then I will call nu n j of t the quantity. So it is essentially as before, the sum from I equals 0 to k n t minus 1 of the quantities Fn u y, Fn u at, of course, not y, but jn theta I. And the sigma quantity is defined in the same way, but you put a square here. So we see that I'm writing down the same definitions as before, except that the Q here is the tail distribution of the aggregated jumps instead of just the tail distribution of one variable. So we want to proceed as before, and we want to replace Gayrard and Resnick's conditions by two conditions. One, a mixing condition, and use this mixing condition to reduce our problem to strong laws of large numbers in the random environment. And we can do this. And so I'm trying to shorten everything because I have 20 minutes left, so I'm trying to compactify what I wanted to say. So, okay. So the sufficient conditions we will get, so doing this, that is using the mixing condition to reduce our conditions to laws of large number in the random environment. I'm telling you what we arrive at without going in the so still, since this is written on the blackboard, so we start from this condition. We rewrite them. We simply use this z and just calculate what these quantities are, and we arrive at these things. Then Gayrard and Resnick conditions, they become that this new j converges as n diverges in low to the tail of the measure nu, and this condition becomes that this must converge in low to 0. Then what I'm telling you is that we will proceed as before, use the mixing condition. And what I'm telling you here is general. So that's what I wanted to write, but because we will need them, these conditions, tomorrow for a completely different process. I mean, this will not be a simple random walk, but we can do that in general when we want to check these conditions, prove a mixing condition for your underlying process, J, and use it to reduce your condition to strong laws of large numbers. And this you can always do, and let me just give you the result. So the first thing is to prove a mixing condition. Let us suppose that this is done with, how should I call it? This little kappa. So suppose we prove this one property, and then and then use it to reduce your earlier conditions too. Then reduce the conditions too. So these conditions we will get are, let me write them down, ut u infinity. So I define this to be k and t, the sum over x in Vn of pi nx qu n x. The first condition will be that this must converge to u, the tail distribution of nu. And the second condition is the same thing for t. There's a square around this quantity, and it must go to 0 for all u positive. Let me call this condition C1, and C2. So we just proceed as we did before, but and arrive at conditions. So now, yes, I'm trying to not shorten things too much. So if I can prove a mixing property, then I can reduce my conditions to just laws of large numbers in the random environment. But now I pushed my difficulties inside this queue here. So let me just state the theorem. So under the same assumptions on nu of Resnick and Durez theorem, if there exist sequences an, cn, and theta n larger than my mixing time, but much smaller than an, for which the conditions C1, C2, and we should not forget the condition A3 that is always there, are satisfied, hold, either P almost surely in the random environment or in P probability. Then the blocked clock process converges to a stable subordinator, S infinity. This convergence is in D, in the J1 topology. And S is, as usual, S is a subordinator with Levy triple 0, 0. So I want to bring your attention to the fact that this statement here, that SB converges, is strictly, that it converges in J1, it's strictly stronger, so it implies the statement that the original process, without blocking, converges to the same limit in a weaker topology. But this statement is strictly stronger than this one, because this topology is strictly stronger than the M1 topology. And what we need is really to be able to say that jumps in the limit of the process are matched by a converging sequence inside the converging process. So this is really what we need to later be able to control correlation functions. So I would like to tell you the result. The theorem we can prove and then just give you, but I doubt I will have time to, ideas of proof. So the theorem we get is as follows. So there exists a function xi p, which is satisfying that it is bounded below by 1. And the limit as p diverges of xi p is equal to the critical temperature of the REM. So such that in the domain dp of the epsilon beta parameters, so the definitions are the same as yesterday. Epsilon is, I will remind you, epsilon was the parameter that enters the definition of intermediate scales. So in a domain of so this characterizes my time scale, and this characterizes, of course, my temperature. And I'm asking that beta is smaller than the minimum of beta c of epsilon that was defined yesterday, and psi p. So we can check that the ratio of beta to beta c here is smaller than 1. Then there exists a constant, kappa, that depends on p, but also on epsilon and on beta, such that taking kappa as 2 to the n squared, so this is the little kappa from here. Then, it's not this kappa, the theta is the blocks, taking the blocks like the kappas. SB, the blocked clock process, converges in J1 to, let me call it S intermediate, because we are on intermediate timescales, where S intermediate is a Levy process subordinator. With Levy triple as usual, 0, 0, new intermediate, and new intermediate of u infinity is, so cap p of epsilon beta times alpha of epsilon u to the minus alpha of epsilon. And this holds, this convergence holds p almost surely if p is larger than 4 and in p probability if p equals 3 or 4. So this theorem is a joint work with Antoine Bouvier. And the first convergence results for a clock process for the Pace-Pinesky model was proved by Gayrard, Benahous, Antoine Bouvier, and Hergé Tcherny, but they obtained a result that was averaged over the random environment. So the techniques that I am presenting here, they are really much stronger because they allow you to get strong results, P almost sure convergence in the J1 topology. So unluckily, I won't have time to tell you much. I didn't plan to tell you very much about the proof, but just a little bit. So again, we see that the limit is a REM-like trap at low enough temperature. This temperature converges, this critical temperature converges to that of the REM as p goes to infinity. So as p goes to infinity, we get back the REM result that I presented before. So the morale of the story somehow is that the random walk, when it walks in its landscape and when the time scale you choose is short enough, it's exponentially large, so it's not very short, but it's not the maximal time scale. So you are on intermediate time scale. Then, in fact, the part of the random environment that it is allowed to explore is, so you remember the picture I made before, these big lumps, they are statistically independent. And so they don't feel strong correlations. So the strong correlations in the Pace-Pinesky model, they arrive when you start looking at extreme scales, which give you the scale of of Gibbs measure, of the equilibrium measure. But before, when you look at much shorter values of the Hamiltonian, the shorter the time scale is, and the more these values become independent. This was something that was observed in physics by Barker and Mertens, where they observed that if you take the order statistics of these big Gaussian processes, so you have the extremes that are very complicated objects, and then you look at what happens in the bulk of your order statistics, and what you see there is exactly a REM, because the random variables become uncorrelated when you look at the bulk of small random variables. So here we are not really in the bulk of small random variables because they are still large ones. The time scale is exponentially large, but it is still far from the extreme, and there's enough independence emerging here to be able to precisely get this convergence. So just briefly with words, the idea to prove this. So you have to prove the convergence of your you have to prove strong laws for these quantities here, where Q is the tail of your aggregated jumps here. So you are working with small windows of size n square. So the idea here, first of all, I will not work with this quantity because it's quite hopeless. So I will take parts to Laplace transforms, and instead of having to work with tails of laws, I will work with exponential moments, which gives me a little more freedom. And then I will use a comparison, Gaussian comparison method, which is what you do when you have Gaussian processes. The Gaussian comparison techniques tells you that you take your reference process, which for us is take the walk on the jump chain on the length theta n, and look at all the Hamiltonian variables, look at the taus along the walk, and take this to define a Gaussian process, a one-dimensional Gaussian process. So I take my collection of random variables along my walk. It defines my reference Gaussian process in one dimension. And then my comparison process is something simple. So it is a process with covariance matrix. So let me call it lambda. It is 1 minus 2p divided by n if I take 2 points I minus j, such that, so I will tell you what L is after. So I will further split, so we take the chain Jn on a block of length theta n, and I split my block into little blocks of length L that are of the form n to the power rho for rho smaller than a half. And I take for, so my reference process is the Hamiltonian along this walk, and the comparison process is a Gaussian process whose covariance matrix is 0 between two little blocks, different little blocks. So the covariance between this block and the next one is 0. And it's non-zero inside one block. That is what that means. And why this choice here of the covariance? It is because if you look at the definition of the covariance of the Pace-Pinesky model, well, you see that the pth power of the overlap is well approximated by the covariance I wrote there when the points are close, because this quantity is small, and if I take 1 minus 2 to the n, a small thing to the power p, then it essentially behaves like 1 minus 2p to the n times this distance. So this is my comparison process. And now Now I apply Slepian's lemma, or perhaps you call it something different, that enables you to compare the difference between, compare two Gaussian processes using it's a formula that gives you this comparison using only a function of the covariance. And then the very nice thing is that this comparison process you wrote here, it turns out to be a stationary Gaussian process. And stationary Gaussian processes are very well known, and they have a very nice representation in terms of independent random variables. And then using this representation, you can actually do calculations. So I won't tell you that it is easy, because it takes a little bit of courage doing them, and it's very many pages. But it is just feasible, because in the end, you are manipulating functions of independent random variables. So this is basically the story. Now, I just want to conclude by telling you I'm not writing down the two-time correlation function, but of course, the two-time correlation function we used so far, the probability not to jump inside a time interval, it makes no sense here, because actually the process is not expected not to jump. When it is inside one of its lump there and it crosses, it is expected to move and visit this point successively. So you have to use a different two-time correlation function. And this is what I told you during the very first lecture, that you sometimes have to use for two-time correlation functions quantities that are a little bit more general. And here, a nice thing to do is to take the probability that the overlap between, so R, between the state of the process at time C and TW, and the state of the process, so the overlap between the state of the process at time TW and at time TW plus T is large. You want to see this, it's the same as saying that the distance between the state of the process at time C and TW and at this other time point is small. And because the other probability is just 0, the probability not to jump. Then you use this quantity here, and because you did little blocks, then you cannot deduce the convergence of this correlation function simply from the convergence of the clock, because you have to deal with the little blocks. So it takes a little more information to control what the process will do inside little blocks of length theta n. So this takes a little more information on the jump chain and on the local information on the random environment. So there are two things into proving aging. One is getting convergence of a suitable clock, which is what we did. And the other one is to prove convergence of the two-time correlation function, which does not come for free in a typical model. If you only have everything independent, random environment, random walk, etc., that's okay, good. But otherwise, it's typically not the situation, and you have to deal with that. So perhaps tomorrow I will have time to tell you a little bit more about this, but I suppose I was, which time was I supposed to finish? Was it, is it correct? Okay, because nobody complained, so I thought perhaps I'm finishing too early.